he mentions a little later here. Well, not here, but eventually. I'm not sure if this is due to Poincare or not, but let's see here. Where was I? U goes from what to what? U is from I to S1. So from the unit interval to the circle, unit circle. And U of t is what? E to the 2 pi I t. Oh, I'm sorry.
Don't write x, write e.
Yeah, excuse me. What am I saying? That's crazy. That would be e to the 4 pi squared. There, yeah, excuse me.
Should have just said x
Yeah,
of t.
yeah, sorry about that. Yeah. There, better, okay. Yeah.
So here they have dropped the weird exp notation they were using before. Now they're just calling it u. Remember?
That's true. Yeah.
Oh, right. This would be.
Well, u is only defined on.
So you're saying this is actually exp.
Oh, good point.
Is this exp t though?
Yeah, x of t restricted. Yeah.
Restricted to I.
Yeah.
So it's like this. I guess that's why it's not doing that. Funny. Then U eta is a 1 cycle in eta 1 in S1. And we saw in exercise 3.2 there's a map from S1, map f prime from S1 to x, making the following diagram commute. So we have I, we have U, we have S1, we have the f prime map by the exercise we haven't done, we have f. I mean, I can't speak for myself. I mean, I only speak for myself. Maybe you guys have done it, I don't know. So this diagram commutes, in other words, what? I guess this diagram commuting would mean f is equal to what?
F prime.
Yeah. And then he says f prime induces a homomorphism. F prime star from what? From H1 of S1 to H1x, right? In particular, the class of the sum mi sigma I maps to the class of the sum mi f prime composed of sigma I. Right. He says it follows that the class of f eta is equal to the class of f prime. It's equal to fun. Which is equal to the induced map, the prime induced map on the Clausen, which is an element of H1x. Okay. I mean, exercise I haven't done aside, I think that makes sense. But, and then what? He says, assume G is a closed path at x naught, then f is homotopic to G relative to I dot. And by exercise 3.2, we have f prime homotopic to G prime. The homotopy axiom, theorem 4.23. All right. Thus gives that the class of Fn is equal to the class of Gn. Therefore, phi is well defined. So for this to be well defined, if we have two different representatives of the fundamental group here, right?
Right, that's about the same thing.
map to the same, to homologous one cycles. One chains, I should say. Oh, one cycles is right. Oh, I can call them one cycles in here. This is what I keep getting confused about. In here, everything's a cycle. Some of them are boundaries, some of them are not. But everything's a cycle.
Right.
But when we're talking about SNX, those are n chains. Those don't have to be cycles, right? Duh. So, oh man. So he says, lemma 4.26 may be paraphrased. Homotopic closed curves must be homologous. This mapping phi is called the Hurwitz map. It gives us a homomorphism from the fundamental group based at x naught to the fundamental, to the first homology group of x, right? There's this triangle, this mysterious triangle argument. That's
Good old mysterious triangle argument.
Mysterious triangle argument. He then introduces the substitution principle, which is another really cool linear algebra result for modules, right? And then finally Hurwitz theorem. If x is path connected, then the Hurwitz map, phi, is a surjection from the fundamental group based at x naught to the first homology group of x. With kernel, the commutator subgroup of the fundamental group based at x naught. So he puts a prime on that.
Mm-hmm.
That means the commutator subgroup. Hence, the quotient. Here's first isomorphism theorem at work. The quotient of the fundamental group by the commutator subgroup of the fundamental group is then isomorphic to the first homology group. And the proof's about a page long. 2 pages long. But it's pretty stuff. And then finally we learned that the first homology group of the circle is the integers. And that if x is simply connected, then the first homology group is 0. Those are for free because we know the fundamental group of the circle is the integers, and the integers are abelian, so when you look at their commutator subgroup, you know, what is the commutator subgroup? What is the commutator subgroup? I don't know if I know what the commutator subgroup is. Is it like, for a group, is the commutator subgroup something like G, H, G inverse, H inverse, such that G and H are in the group?
I think so.
So that's like he would say G prime. So for an abelian group, that's 0.
Yeah.
So nothing is lost when you quotient by that. So the fundamental group being the integers, we almost proved that in another lecture. We have seen the pages in Rotman where he suffers through the proof of the fundamental group. I mean, it is involved to prove the fundamental group of the circle is the integers.
Well, we showed that.
We came pretty close to that.
That was when I lectured.
Yeah, we were actually pretty close to that. I think there was like only one lemma we skipped on, if I remember right. But I think you're also right, Nathan, that in a good complex analysis course you could prove it without much work once you get to a certain point in the course. Anyway, you're right. I think that's also true. But anyway, so that's why the first homology group of the circle is Z, because it's isomorphic to the fundamental group of the circle, which is also Z. And likewise, if the fundamental group is trivial, then when the quotient is not, it's still 0, and so that means the homology group of any space that's simply connected is also 0. At the first level anyway, the first homology group. I don't know about 2 or 3 or other things, but at least the first one. And then finally he talks about polygons. A polygon in a space X is a one chain where the they start and end kind of like where the first one, where the ith one ends, the next one begins, right? And then I think they have to loop back. I think that's what he's saying here, right? I would assume it has to loop back. I don't know.
Yeah,
Otherwise,
yeah,
it probably
it talks about mod k plus 1.
mod k plus 1. And he has a theorem here. A chain, a one chain is a cycle if and only if it's homologous to a linear combination of polygons. So that seemed to me to be a very geometrically satisfying statement, right? And then finally, Nathan is up next, and he'll be talking about the homology functors, long exact sequence, and excision. And as you had pointed out, Nathan, the chapter beyond that one is the one where we'll actually start
Wait,
calculating.
excision? I'm just doing chapter 5, aren't I?
Oh, wait a minute, what is... I thought chapter 5 was...
Chapter 5 is just long exact sequences.
Oh, excision's the next one.
Yeah.
Excision, I think, is the one where...
That's where you get some of the...
Yeah,
Like, they calculate the homology
Torus
groups
and-
of spheres.
Yeah. Chapter 6 is where we actually finally calculate something, so hopefully we'll get there before too long. Anyway, have a good break, you guys. Thank you for your patience. Sorry I don't have more time to spend on scores.